Hello, and we're going to talk about gravitation today. We've really been talking about gravity all semester, really, but we haven't really been using the most generally applicable version, okay? And so we're going to improve our tool set here. And it's worth saying that really we've been using a very specific form of what's known as Newton's universal law of gravitation, which rolls off the tongue nicely. And we've been using a form of it that's very accurate for an object that is relatively near the surface of the Earth. And we'll see sort of what I mean by relatively near the surface of the Earth and the importance of that little qualifying phrase in a little bit. Okay? And here it is, right? F sub g, the force due to gravity on an object, is equal to the object's mass times the acceleration due to gravity. And we just plunk down 9.8, sometimes 9.81 if we're feeling particularly accurate, meters per second squared for the acceleration due to the gravity of the Earth. And we recognize that that's not sort of a universal constant because, one, I've told you it only applies near the surface of the Earth. I've also placed us on, the moon or Mars or something like that for certain questions. And G there is a little different, okay? So we know that that's sort of specific to a particular planetary body, at least. But let's look at where it comes from, okay? So if we fit it into the general form of Newton's universal law of gravitation, it looks like this, okay? So bound up, so we still have the same old F sub g, and we still have the same old mass of the object, but bound up in this g, that acceleration due to gravity that we just call 9.8 meters per second squared, is all of this stuff, okay? So we have the mass of the Earth, which is on the order of 10 to the 24th kilograms, big. The radius of the Earth, which we're not a perfect sphere, but we're reasonably close. And so this is like 6,080 kilometers, so 6.38 times 10 to the 6th meters squared, okay, as you can see right there. And then this mysterious, maybe not so mysterious, constant g, okay? This is known by a couple of different names, but the gravitational constant is one that you can use. And the numerical value of it is this doozy right here. It's a tiny little thing. It has units that essentially just make the units here work out, right? You have... What would it be? So it would have to be newtons, and then it would have to be divided by kilograms squared, and then it would have to be multiplied by meters squared. Yuck. Okay? But in any case, the numerical value is the thing that you'll actually be doing calculations with. Okay? So all of that is bound up in that little g that we have in our old version of f sub g. Okay, so why are we talking about this? Well, we're going to talk a little bit, or perhaps we have already if you've been to lecture lately, of circular motion problems where we are considering, for example, the Earth going around the sun. And obviously, the force of gravity that is giving the Earth the necessary centripetal force and thus centripetal acceleration to stay in its roughly circular orbit around the sun is coming from gravity, but that can't be just mg, right? Because one, we're not anywhere close to the surface of the sun, so we can't just like define a different value of little g very easily. And in addition, we can't just plump down 9.8 meters per second squared because that's specifically for the Earth and the force on objects near the Earth's surface, not force of gravity of the sun acting on the Earth over these colossal distances between the sun and the Earth. Okay? So we need this tool. We need Newton's universal law of gravitation to deal with that. Now, this is for a specific example, right? This is Newton's universal law of gravitation for an object near the Earth's surface. The general version of it looks like this, a little cleaner, okay? And what this is telling us is that the magnitude of the force of gravity, okay, between two objects, is equal to that big G that I mentioned, the mass of the first object times the mass of the second object, divided by the distance between their centers of mass. Okay, so what does that mean? Well, I've got an example, a little diagram here. If you had two objects and one had mass 1, the other had mass 2, and the distance between their centers of mass, well, if these are uniform objects, so like a ball bearing of steel or something like that, well, then the center of mass is kind of like the average position of all the little bits of mass that make up that object. And so for something that's uniformly shaped and has uniform density like those things, then the center of mass just is right in the middle. And so R is pretty easily measured. Because it's worth mentioning, even though the radius of the Earth is kind of a rounding error when you compare it to the distance from the Earth to the Sun, it is a small correction, right? We want to measure all the way to the Earth's center of mass, which is approximately in its center, and all the way to the Sun's center of mass, which is approximately in its center, to accurately measure R. Okay? So, that's gravitation in a nutshell. It is always attractive, these forces. So if we're drawing our forces on here, let me do that, we would have a force of the second object on the first, which would be exactly in line with that line separating their centers of mass. So that would be like force of gravity of mass 1 on mass 2. Put it in subscripts if you like. And then that same force, remember the third law tells us that that same magnitude of force, just opposite in direction, is going to be pulling on mass 2. And that would be the force of gravity of the first one acting on the second. Okay, so F sub G12. You can denote it any way you like, but that's the basic idea. So gravity is always attractive, okay, and it has a magnitude that is given by Newton's universal law of gravitation. A couple other notes here. One, this is still not the best model of gravity that we have. Einstein improved upon Newton's universal law of gravitation as recently as just over 100 years ago. And the general theory of relativity, however, requires quite a bit of mathematics that we aren't going to be delving into in this course, but does allow us to explain some gravitational phenomena that Newton's universal law of gravitation doesn't do too well, okay? But Newton's universal law of gravitation is a surprisingly powerful tool in predicting the orbits of planets and the trajectory of spacecraft and the behavior of objects near the surface of a large body like the Earth or the Sun or another planet or anything like that, and still has great predictive power in that respect. Okay, and so we'll be using it for modeling our gravity between two objects that are relatively distant, and specifically objects that are not near the surface of the Earth, like most of our objects are. Okay. Now, as for relatively near the surface of the Earth, well, if you go to the top of Mount Everest, get as far as you possibly can without actually leaving the ground from the center of the Earth, well, as it turns out, that doesn't really change little g very much. Maybe by a part in 100 or something like that at best. Where you actually start running into significant deviations from it, where you can really ought to be breaking out the general version rather than this version, okay, would be for spacecraft. I mean, the International Space Station is hundreds of kilometers up there, and now you're talking about a significant fraction of the radius of the Earth, which, if you remember, is like just over 6,000 kilometers. Okay? And so when you're changing this distance between the object and the center of mass of the Earth, well, then you need to consider that extra distance in your calculation, and that's when you break out the general version of the law of gravitation. Okay. One other thing before we go. This was tested by a guy with the last name Cavendish, very famous British scientist, has a famous physics laboratory named after him over there in Britain. And Cavendish came up with a very clever experiment that essentially had two masses, one very massive, so sort of akin to M2 over here, and then one that was attached to a very complicated torsion balance, where the gravitational attraction here between M1 and M2 would actually cause this whole sort of hanging apparatus. Okay, so we had these two masses, then we had the big mass over here, to deflect, so rotate around this hanging cable, just a little bit, just the tiniest little bit, because we're talking about masses that are like human scale. And unless you have a ton of mass in one place, like the Earth or the Moon or the Sun, then gravitational forces are actually quite weak. Okay? You need a lot of kilograms of stuff to have them add up to any significant number of newtons. So even for the relatively large mass metal spheres that he was dealing with, the forces of attraction between them were really quite small. Tiny, tiny little things. And so that caused the whole thing to deflect ever so slightly. And you're wondering, oh, well, how would he measure it if it was so tiny of a deflection? Well, what he did is he had a light source and a mirror attached to this thing, and then would project it on a distant wall. And so that tiny, tiny little deflection would actually be measurable once you sort of magnify that over that long distance. You wouldn't be able to measure it if you were just looking up close. So just a little side note. Read up on it if you will, and there's lots of resources on it on the internet. Maybe I'll pick one out and put it on the course webpage. But for now, that's the bare bones version of it. And thanks for listening about gravitation.